Today, we're diving into a really wild process that happens inside semiconductors. It's called Avalanche Breakdown. And honestly, it's like a tiny, microscopic electrical storm. It's a force that can totally destroy a component, or if you know how to tame it, you can use it to build some incredibly powerful electronics. So let's get into how it works. I want you to just picture this for a minute. You've got one single supercharged electron flying through a microchip. It's been accelerated by an electric field and it slams into an atom, knocking another electron free. So now you've got two, and they both get accelerated and they each knock another one free. And just like that, you've got 4, then 8, then 16. You get this massive cascading avalanche of current, all starting from just one particle. That's the amazing idea we're going to unpack.
All right, let's start with the big question. What is this avalanche breakdown really?
Okay, so at its core, avalanche breakdown is basically a form of electric current multiplication. Think about it. Inside a material that's normally supposed to block current, a strong enough electric field can kickstart this incredible chain reaction, and that allows a huge amount of current to suddenly flow where it normally couldn't. It's a fundamental process that happens when things get really, really energetic down at the atomic level.
And this graph right here shows you exactly what that looks like. Now focus on that IV curve. As you increase the reverse voltage, that's the voltage pushing current the wrong way, you can see that basically nothing happens. The current stays flat right at the bottom. But then you hit that breakdown voltage and bam, the current just shoots up, almost vertically. That sudden spike is the avalanche.
So how does this whole cascade actually get started? Well, the physics behind it is a process called impact ionization. Let's break that down.
Impact ionization is pretty much exactly what it sounds like. You have an electron, and it's been supercharged with kinetic energy from that electric field. It literally impacts another electron that's just sitting there, bound to an atom. The collision is so energetic that it knocks that second electron loose, creating what we call an electron-hole pair. And now you have a new free electron plus the hole it left behind, and both of them can carry current.
And here's the crucial part. This is how it becomes a chain reaction. That one electron gets accelerated, it gains energy, and it creates a new pair. But now there are two free electrons, plus a mobile hole. They all get accelerated, and they can all go on to create even more pairs. This thing just grows exponentially. It's a beautiful and incredibly powerful cascade that creates that massive current spike we saw.
And you know, this isn't just some abstract theory. It's absolutely fundamental to the field. This quote comes from S.M. Zai's Physics of Semiconductor Devices, which is basically the Bible for this stuff, and it just nails the core idea. It's all about one energetic particle having enough punch to create another, and that's what kicks the whole thing off.
Okay, so we've got this unbelievably powerful effect. But, a sudden massive rush of current, that sounds a little dangerous, doesn't it? And yeah, it can be. This really brings us to the two faces of the avalanche. It can either be a total catastrophe, or it can be an absolutely brilliant design feature.
So if this avalanche happens in a device that isn't built for it, the results are almost always bad. That huge spike in current generates a ton of heat in a tiny space. This can cause the electric field to concentrate in one spot, leading to thermal failure. Basically, the component just melts and is permanently destroyed.
This simulation gives us a great look at those danger zones. It's showing the electric field inside a diode right at breakdown. See those bright red areas? That's where the field is the strongest. And that is exactly where impact ionization is most likely to kick off, creating these little hot spots that can lead to catastrophic failure if they're not managed.
But here is where it gets really clever. What if you could actually control that breakdown? What if you designed a device to not just survive the avalanche, but to actually operate inside it? Well, engineers figured out how to do exactly that, and they turned this destructive force into something incredibly useful.
And that brings us to the iPad diode. These things are amazing. They're specifically designed to live in avalanche mode. And because the avalanche is almost instantaneous, it allows for incredibly fast switching. That speed is perfect for generating really high-frequency signals, like microwaves. We're talking about the tech inside police speed guns, in satellite communications, and a power output is just staggering. They can produce signals in the kilowatt range, all by perfectly taming this avalanche effect.
Now, if you've ever messed around with electronics, you might be thinking, hey, this sounds an awful lot like a Zener diode. And you know what? You're on the right track. They're related, but they're definitely not the same thing. This is a super common point of confusion, so let's clear up the difference between avalanche breakdown and Zener breakdown.
This slide lays it all out pretty clearly.
The single biggest difference is the mechanism. We know avalanche breakdown is all about high-energy collisions. It's a physical process. Zener breakdown, though, is based on a mind-bending quantum mechanical effect called tunneling, where electrons can just pass right through a barrier they shouldn't be able to cross. Because the physics is different, the operating conditions are different. Avalanche breakdown usually happens above 5 or 6 volts in lightly doped materials, while Zener breakdown takes over at lower voltages in heavily doped materials.
So when we look back at our IV curve, it's pretty cool to realize that while the end result looks almost identical, that sharp vertical line where current suddenly flows, the physics driving it can be completely different depending on the device. It's a fantastic reminder that in physics, sometimes two totally different paths can lead you to the exact same destination.
So really, the story of avalanche breakdown is all about taming a force of nature. It starts out as this microscopic storm that can tear a circuit apart, but with some clever engineering, it becomes the engine behind some of our most powerful technologies. And that just leaves you wondering, right? How many other seemingly destructive forces are out there, just waiting for the right design to turn them into the next big breakthrough? Thanks for tuning in.